a line charge distribution, a sheet of charge, or a volume charge distribution. Since it is difficult and impractical to work with discrete charges in terms of the microscopic locations of the charge distributions, to evaluate the electric field at a point, we adopt a different approach. In such situations, the entire charge distribution is assumed to be made of infinitesimally small elements, and the electric field strength at any point in the electric field will be equal to the vectorial sum of the electric field strengths due to each such small element. Let us look at a line charge distribution of length L carrying a charge Q as shown. If we consider a small element of such a charge distribution having a charge delta Q and of length delta L, the linear charge density, lambda, of such an element is equal to delta Q by delta L, since it is the charge per unit length. The SI unit of linear charge density, lambda, is Coulomb per meter. It is a scalar quantity. If a line charge distribution is carrying a non-uniformly distributed charge, then its linear charge density, lambda, for an individual element is equal to delta Q by delta L. If a conductor of length L is carrying a uniformly distributed charge Q, then its linear charge density, lambda, is equal to Q by L. Now let us consider a sheet of charge carrying a total charge Q on a surface area A. In such situations, the electric field strength at an imaginary point P can be calculated by assuming the charge distribution to be divided into infinitesimally small areas, each having an area delta A and charge distribution delta Q. Surface charge density, sigma, is the charge per unit surface area. Therefore, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. It is a scalar quantity measured in Coulomb per meter square in SI unit. If charges are non-uniformly distributed, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. If the charges are uniformly distributed over the surface, then the surface charge density, sigma, is equal to Q by A. Now let us consider a volume charge distribution. Consider a volume V carrying a charge Q. Let us assume that the total volume is divided into a number of small elements, each of volume delta V having a charge delta Q. Then, volume charge density, or charge density, ρ, of such a volume charge distribution is defined as the charge per unit volume. Thus, ρ is equal to delta Q by delta V and is measured in Coulomb per meter cube in SI unit. It is a scalar quantity. If charges are not uniformly distributed, the charge density ρ for an individual volume element is equal to delta Q by delta V. If the charges are uniformly distributed, the volume charge density of the conductor is expressed as ρ is equal to Q by V. Now consider the small volume element delta V of charge distribution carrying a charge delta Q. We know that the charge density ρ is equal to delta Q by delta V. Thus, charge on the volume element is then delta Q equal to ρ delta V. The position vector of the volume element delta V with respect to the origin O is R. Consider a point P in the electric field of the volume charge distribution. which is at a distance of r dash from the volume element delta V. The electric field strength at point P due to the volume element is delta E is equal to 1 by 4 pi epsilon naught delta Q by r dash square into r dash cap, where r dash cap is the unit vector in the direction of the straight line from the volume element towards the point P. This can be written as delta E equal to 1 by 4 pi epsilon naught into rho delta V by r dash square into r dash cap. Now, the electric field strength E at P due to the total volume charge distribution is equal to the vectorial sum of the electric field strengths due to all individual volume elements. However,